Today I'm going to talk about signal processing flaws in CNNs. First question is, who of you has been using CNNs or has been training a CNN? Quite a few of you. Okay, so that might be interesting for you. Quick introduction of our group. As mentioned, I'm coming from Germany. Fraunhofer organization is a non-profit research organization, a little bit similar to national labs in the US. Fairly large with different institutes around the country. We're from the Institute for Applied Mathematics. And the HPC department within the institute has a long history of doing full stack HPC research. We're doing anything from kind of experimental CPUs and computer architecture to new communication protocols. And kind of one of the most prominent outcomes of our lab has been discussed this morning, which is BGFS, which is actually invented at our lab. Doing HPC actually was kind of natural to also start working on seismic. So we have a large seismic group, geophysicists, working on traditional seismic topics. Like we have our own GRT and RTM codes. We do a lot of industry contract work. And also we have some prominent spin-offs there. Maybe you've heard of Prestack Pro from Sharp Reflections, which is also a spin-off company from our lab. And we're running a quite successful research consortium for several years now. It's called Deep Learning in Seismic. There are some of the sponsors that have been supporting us for a few years now. Currently, we're focusing on deep learning methods in the pre-stack domain and pre-processing. If you're interested in that, we have a small booth. You can approach me at the coffee break. But today, I want to talk a little bit about more basic stuff, just coming from our basic research. And now I assume that everybody roughly knows how a convolutional neural network is working, because I'm not going to go into the details there. I just printed out the original AlexNet. This is kind of the network that started it all. If you ask anyone but Jürgen Schmidhuber. The traditional structure here has changed a little bit, if more modern architectures, but the basic units still kind of stay the same. So what do you have? You have convolutional operators where the filters are typically learned by some gradient learning method based on your data. You have some nonlinear activation functions, mostly ReLUs, and you have some kind of spatial downsampling. It might be pooling, or it might be some kind of strided convolution. So that's the typical setup you always have. And no matter what kind of architecture you're having, this is going kind of through. And this kind of architecture has been extremely successful on any kind of learning problem where the input or output is kind of dense ND data. Of course, in most cases, kind of natural images. This is what people always show. You kind of detect persons on the street, and you can distinguish a cat from a dog, and so on. But of course, this also works in the seismic domain, where your input data also is kind of ND array data in most cases. So if you look at the success in the past years, and just some of our own publications where we used CNNs, and the most popular architecture in seismic applications actually is UNet. We've seen it today a few times, and if you go through literature, it's kind of the very dominant architecture. The specialty about UNet is that the input and the outputs basically have the same dimensions, so you're not classifying input data into cats and dogs, but you're kind of processing data in some ways. For example, for semantic segmentation, or for horizon tracking, or for other stuff. But there are so many applications now out there. I think someone told me last year at this conference that UNet is already one of the most cited papers in geophysics, which is really surprising because it's just a few years old. All right, so now what's the problem with CNNs? People have been using it, and it has been becoming more and more successful, state-of-the-art architectures, they're using it, and everybody was kind of happy. Of course, there's the obvious downside, like you need a lot of data to train this, the data needs to be annotated, and it costs a lot of compute. But a few years ago, people started looking at these classification processes from a different angle. And you might take it as a security angle, but I personally don't want to pitch this as a security problem. So what did people do? They handcrafted noise, and this is highly amplified. So basically, this is an original input image. You add some noise, and the noise is so low that this is adding the noise to the image. You couldn't tell the difference, right? And adding this noise would cause a CNN to flip its decision. Not only to flip its decision, but also give very high confidence in this fault prediction. This is so-called adversarial attack. So many people might say, well, yeah, that's a new security threat. Now the bad guys are going to start to attack our AI, but what should I care, right? I mean, I'm processing data. There's nobody's coming around and gonna attack me. It's a closed system. Why should I care? Well, I'm going to argue why you should care. Just to show you how big the problem actually is, this is a study we did for NeurIPS 22. And it's actually a large field study where we looked at many publicly available models. And the interesting thing is, now here are the clean samples, and here are some of the attacked samples. The optimum is right here. So basically, you always should do the right decision and be very confident about it. So the problem is when you're up here, then you're wrong and very confident about it. And this is actually what's happening. That non-robust models, so these are models that are tending to flip their decisions based on marginal changes of the input distribution. And this is kind of the key thing. It doesn't need an evil guy coming around to push the input distribution just a little bit. This can just happen because you change something in your recording setup, because you change something in your pre-processing pipeline. Then you have a distribution shift. And then everything can go wrong, and your model will be highly confident about this. So what's the cause for this? Why does this happen? Actually, we only partially know. That's the truth. There's been going on a lot of research in the last 2-3 years because obviously the community is detecting this problem and investigating. And so far, it's not really good understood. I mean, there are some indicators, of course, that most of the models we're using are implicitly overfitting because our test distribution is typically the same as the training distribution, which is not realistic. That's part of the problem. Then we have very high dimensional decision spaces. We have very high nonlinearities in these decisions, which kind of cause some of these problems. But this is not the part I want to talk about today. The part I want to talk about today are actually that some of these problems with robustness are actually coming from inherent problems because CNNs are neglecting some very basic signal processing laws. And this is important to keep in mind. This is not the only source. If you fix this, this does not keep your attacker away. But this is some of the part that will always happen. And that's what I want to shed a little light on. So does this matter to your seismic or other application where you use CNNs? Yes, of course, if this is a publicly accessible model, then the evil guys could attack it. But this is not the thing I want to look at. What I'm more interested in is actually what's happening if you're using your CNNs not as a final decision model in terms of a classification, but if you use your CNN kind of in a pre-processing step in your pipeline. And that's typically what's happening when you're using these UNets. So the input is an ND array, the output again is an ND array, and then you keep doing something with that. And if you mess up the signal processing in there, that will affect everything you do down the line. So where are these problems coming from? Of course, if we have a convolutional neural network, then the convolution is going to be some part of the problem. Actually, the nonlinear activations are also part of the problem, but I'm going to skip this part due to time constraints. And of course, also the downsampling, if you think of it in terms of signal processing, will be a problem. So I'm going to focus on these two parts. So in order to have a closer look at this problem, we started a large field study. This has been published in CVPR 22. Basically, what we did is we downloaded a large number of publicly available trained CNNs for many different tasks. So there were segmentation problems, classification problems, on all sorts of data sets from astronomy, from seismic, from medical, natural images, and so on. In the end, we ended up with billions of trained convolutional filters. And then we did a large-scale analysis on them. And there are two things to report. First, the good thing. The good thing is that all of these trained filters appear to be coming from the same distribution. No matter what the data source was, no matter what the task was, no matter what the architecture was. And that itself is very interesting and kind of explains that what many people do in practice actually works, is that you pre-train on some other data. So have you ever tried pre-training on some natural image data and then apply to seismic? Why should this work? Well, it does. It actually is because they are all coming from this kind of the same distribution, plus minus scaling a little bit. So that's the positive side. The negative side actually is that there are many things wrong with these even very successful publicly available models. And one thing is that a large portion of these filters that the networks are learning are actually degenerated. They're basically close to zero, or they're the same all the time. Why is this happening? Because they actually don't get any gradient. So you spend a lot of compute, there's discussion this morning, a lot of matrix multiplications where you actually don't have any gradient, and you end up with large portions of the model being not used. This is not new. There's a thing that's called the lottery ticket hypothesis that explains kind of you need these oversized models to have a better chance to find a smaller solution within the network. But if you keep the network large, you just need to have a data set that's going out of the path in one way, and you're ending up in totally uncharted territory. So one thing you actually should do is to prune these networks before you use them. So pruning, there are a lot of standard techniques, and we actually showed that, that this helps. Another thing we looked at a follow-up is actually, if you look at the architecture of these networks, they talk always in channels. So typically, if you have an RGB in it, you have 3 input channels. Maybe in seismic, it might be 5. But it's rather low number. And then they increase the number of channels. And then you apply these filters. And typically, what's happening is that you're actually losing a lot of information early on because you're applying these filters. And this is really hurting. And what we did here is we looked at what's the difference between robust models and non-robust models. And actually, it's in the very beginning and in the end of the networks. And that's typically because here a lot of information is lost, and here there's simply not enough training data to train all of these filters. And what's actually very interesting is that if you look at adversarially trained networks, that's basically using these attacks for augmentation to generate more data, and to then train robustness against this specific attack. It always needs to be noted it's only this specific attack. That these networks actually learn a first layer of filters that doesn't do anything but replicate the data. So you get more of it, kind of to rescue it from the filtering. So if you look at these filters, it's just basically not filtering anything. It's just a weighting of the filters. So. OK. Then one thing we did is we did a lot of things with generative neural networks, especially trying to embed simulated data into real seismic to get ground truth for segmentation problems and so on. And one thing you really want to make sure is that the data you generate kind of meets the distribution of the data, of the natural data, right? And we looked at different parts of it, and one thing we also did is we looked at the Fourier spectrum of the data. And one thing we saw is that actually gun-generated data highly differs in the Fourier spectrum from natural data, from seismic data, from lateral images, and so on. And we couldn't fix it. We tried all kinds of things, and we could not fix it. And then we looked into it, and actually the problem is that using these small convolutional filters, also in your UNet for these up-convolutions, you have a very strong band limitation. And then you build these pyramids of band-limited filters. And this actually, you can see it here, where you have these repetitive patterns where the band limitations at different scales really kick in. And now, if you assume that your normal signal looks something like the purple one here, and your generated one looks like something like the yellowish-greenish one here, if you have some downstream analysis that really relies on that the spectrum is right or that the frequency distributions is right, then you have a real problem. So another thing is, and this is actually not from us, so other people are also looking in this, but it's a very interesting result, is also that the same thing when you have these small filters, you kind of end up with these windowing effects. So basically what this is just is the filter using very small one and the same one kind of embedded in a larger, and you take the Fourier transform of it, you can see that due to the windowing, you get all kinds of these artifacts. And that's also an effect that really turns in. So small filters are very popular because they're computationally efficient. You have these hardware accelerations for it, but actually they induce all sorts of signal processing flaws here. Okay, another one real quick. When you do convolutions, you also need padding. And the question is, should I use padding? Should I use zero padding? Should I use cyclic padding? And so on. And here we also did a study, and the results are actually in a way that any kind of padding is quite bad, but zero padding is still the best. So everybody's doing it right, unintentionally probably, but still there's some heavy artifacts in there. And if you look at where are the attacks actually attacking, depending on the padding you have, you can actually see that if you have zero padding, they kind of try to alter the center, while if you use other paddings, they kind of go to the borders and use the padding for the advantage of the flipping. Okay, so second block, now we have the convolutions. Now we always need this upscaling and downscaling. In the UNet, I have downscaling on one side and upscaling on the other side. So we already talked about the problems using up convolutions for upscaling. Let's talk about a little bit about downsampling. So what's very common is just to use pooling. So pooling basically is just interpolation, and typically by a factor of 2. Sometimes, in most cases with a maximum pooling, so you just take the maximum out of a neighborhood. And that actually induces a lot of aliasing in what's happening downstream. So in a pure classification network, that might not matter because you're not seeing that. But if you look at it from a robustness perspective, actually we could show that if you induce aliasing in your network, in the processing, the robustness is really going sideways. And a nice way to fix it is actually going back to signal processing 101. Look up is how do I do downsampling without aliasing. You'll find, well, you can do this in the frequency domain via frequency masking. And basically we implemented that. Very simple, and you can actually do that without a lot of overhead. So the main concern of people is it going to be very expensive? No, it's not. It's maybe 10% more expensive than doing it the typical way. But if you do that, you actually get much more robustness in your network, and it's rather easy to implement in both ways, both in downsampling and in upsampling. But you need to take care of it. Okay, so now we have all of these problems. How do we actually solve them? What's the practical impact of this? And the first take-home message actually is you need to monitor what you're doing, especially if you're using UNet-style networks that produce output that's being used for follow-up processing. Then you really should have a look at it, look at the frequency spectrum, look at other distributions that might be important for your downstream analysis, and not just look at it and think, well, it looks okay to me, because you don't see these changes in the spectrum, but all your analysis methods downstream will notice the difference. The next thing is use larger filters. That's easily said, because using larger filters makes things more expensive. But actually there is a trend in the community. So lately there have been a lot of publications on using larger filters. For example, the ConvNext, which is kind of state of the art, actually beat transformers last year on many classification tasks. So using larger filters gives you better performance and gives you the security at, again, the cost of more computation. And maybe that's something more for the hardware people. Now NVIDIA has optimized 3x3 convolutions. better you should also optimize 7 times 7 or 9 times 9. Okay, the next thing is use regularization. You can actually fix some of the problems you get in the frequency spectrum by adding additional regularization. So that's one thing we did, and it's actually not so hard. So if you just add an additional regularization term and tell whatever net you're using to produce this output, but my spectrum needs to be okay. And there you really need to be aware. Is the phase important? Then of course, then only regularizing the spectrum is not doing the job. So that's an option. And another very intriguing thing is that if you look at generative neural networks, so lately diffusion models have been very popular. If you look at the frequency properties of diffusion models, you actually see they don't have that problem. So it's a very GAN and UNet and variational autoencoder specific problem where you have the convolutions. Here you see perfect match of the spectra. So that might be one way to go. And the last thing, adversarial training. Of course, again, this is expensive and it doesn't solve anything. But if you know that you're running into problems, it's always wise to use kind of a data augmentation in this direction during the training, kind of to fix this. Okay, to wrap this up, the take-home message from my side is, even though CNNs are a quite powerful tool, you have to be careful, especially if you use them somewhere in your processing pipeline where correct signal processing has some meaning, especially if you use maybe for some pre-processing in the pre-stack domain and then you move on to some other analysis methods and so on. There you have to be very careful. I think the attacker perspective is not that interesting. If you were more working in the automotive industry, then these guys have a much bigger problem with that because their attacks are really realistic and they also have to fight with that. And that, I'm open for discussion.
Thank you, Yannis. We have a few minutes for questions.
I got one. Just a quick one. Good presentation, Professor. Welcome to Houston.
Thank you.
Just speaking my name is Azman Hassan, and I'm a student of Andrews Robinson, if you know of him. He just passed recently. He's the guru of the digital signal analysis at MIT. And anyway, part of the signal when you speak about the spectrum in the frequency domain, Fourier domain, is the phase spectrum. How's that in this picture?
Actually, we haven't analyzed.
Because it's half of the information, actually.
Yeah, it's half of the information. But of course, it's much harder to interpret than the power spectrum, right?
Because they don't do the unwrapped phase.
Yeah. No, but this.
Otherwise, it's going to be up to 90, I mean, up and down, limited. You know, so it's very hard to interpret unless you unwrap it.
Yeah, but it's
Any
definitely.
idea on that?
Well, we're definitely looking into this, especially because we want to make sure that the diffusion models are not making their mistakes there, right?
Right.
So that's something we're looking at. But so far, I don't know a lot of work
So
on
what
it.
I take it from you, it's in the works.
Yeah.
All right, great.